Good day, everyone. I am Monome Ejoromedogene, and I will be given a brief presentation on the paper titled Deep Eutectic Co-Solvent Mediated Surface Enhanced Photochromic Property of Tungsten Oxide Doped Titanium Oxide Heterostructures. In the introduction, over the years, the exploration of novel photochromic materials is beginning to gain so much attention in scientific research due to their promising potential for application in different devices such as smart glasses or smart windows, in optoelectronics, in colorimetric sensing, amongst other applications. However, inorganic composite materials, they have been exploited in this field because they possess tunable morphologies, dynamic functionalities, and intriguing photo switching property. Typically, the tungsten oxide is a semiconductor that have been widely explored in this area. It is imperative to mention that pure tungsten oxide is often characterized by a slow photoresponse, which has hindered its wide application in many areas. However, numerous strategies have been developed to enhance the photochromic properties of single-phase tungsten oxide, including the surface or structural modification of pristine tungsten and elemental doping with other metallic groups to form hybrid composites. Studies have shown that composite materials designed by coupling tungsten oxide with another semiconductor having an appropriate band position can significantly improve the photoresponsiveness compared to the single-phase component alone. Importantly, deep eutectic solvents are a class of ionic liquid that have been used as green solvent towards the preparation of different composite material. They can function as templating agents or suffix directing agents or surfactant group towards the preparation of transition metal oxide-based nanocomposites. So in this work, being inspired by the versatility and improved functionality of tungsten oxide doped with titanium oxide based materials, we intend to prepare an heterostructure under ambient condition. In our strategy, deep eutectic co-solvents were prepared at moderate conditions, and they were employed as a template for the surface modification and enhancement of the properties of the corresponding binary transition metal oxide. The effect of different co-solvents on the structure, the morphology, and the optical properties of the materials that was prepared facilely by solvothermal or hydrothermal method were investigated in this study. In the preparation, the eutectic templates containing 3.4 gram of choline chloride and 1.5 gram of urea was prepared using different co-solvents, which include water, ethanol, and isopropyl alcohol, which were made in separate flasks, and these mixtures they were heated in the thermostated oil baths at 80 degrees for 30 minutes to first obtain a clear solution. Thereafter, 1.0 gram of tungsten salt was directly added to the solution and followed by 0.5 ml of titanium isopropyl to give a colloidal solution. The mixture were allowed to heat and stir for 1 hour, after which 5 ml of glacial acetic acid was used to adjust the pH and give a clear solution containing tungsten oxide and titanium oxide heterostructures after the solution was heated for another 2 hours. The photochromic property of the as prepared powdered materials that was collected after centrifuging and vacuum dry for 8 hours was studied by pressing the samples into a round groove and directly illuminated with 300 megawatts of xenon lamp, which is used as a light source at a wavelength and distance of 365 nanometers and 10 centimeters respectively, and all of this was carried out at room temperature. The coloration of the materials was monitored by measuring the UV absorbance at regular time intervals. The obtained tungsten oxide titanium oxide heterostructures was characterized using different techniques, which include the FTIR, XRD, transition electron microscope, the TGA, the UV visible spectrophotometer, BET for the pore structure of the material, the scanning electron microscope coupled with an EDX, and XPS for the quantitative elemental composition of the material. So according to the FTIR spectra, the vibrational frequency of the pristine eutectic solvent displayed characteristic broad OH and NH overlapping band at around 3423 to 3452 wave number, while the amide C double bond O band at 1634 wave number. More also, the peak at 1554 wave number could be attributed to the NH band and was medium in the ethanol base DES and was very weak in the water and isopropyl base DES, which is a deep eutectic solvent. Meanwhile, the peaks at 1478 to 1456 wave number were assigned to the alcoholic OH band, which could be due to the choline chloride. However, the weak peak at 1802 wave number and 954 wave number could be due to the C single bond O and the quaternary ammonium or the chloride groups respectively. The corresponding metal-based heterostructures were characterized by significant changes in the peak intensity and vibrational frequency, which could be due to the interaction between the metal salts and the deep eutectic solvent. Specifically, the broad OH to NH overlapping band were shifted to 3589 to 3291 wave number, with a very broad band for the water-based heterostructures, while these groups in the ethanol and the isopropyl alcohol-based compound, they appeared at about 3447 wave number. The C double bond O oxygen band, due to the amide, were shifted to 1663 to 1634 wave number, while the alcoholic OH band, the amine C end and the CO vibrations, they were observed at 1473 1162 to 1155 and 1087 wave number respectively. Beside the vibrations that are attributed to be tungsten to oxygen and titanium to oxygen bonds were assigned to the sharp peak at 960 wave number and the broad peak at 591 wave number respectively. Now for the low resolution XPS full survey, it showed that the interacting atoms, they were well represented, revealing the different groups of the tungsten 4F, chlorine 2P, carbon 1S, nitrogen 1S, titanium 2P, and oxygen 1S regions. Meanwhile, the deconvoluted carbon 1S spectra showed three prominent peaks at 284, 285, and 288 electron volts, which could be attributed to the C single bond C, C single bond O, and C double bond O bonds, respectively. In the same vein, the nitrogen 1X revealed an intense peak at 399 electron volts and 402 electron volts, which are ascribed to the organic nitrogen bond of an amide and the C bonded to an amide group, respectively. While the oxygen 1X spectra revealed two peaks in the water and the ethanol-based material and a single peak in the isopropyl alcohol-based material. And these peaks, they were observed at 530 electron volts, which is assigned to the metal oxide bond, and the other peak at 534 electron volts due to carbon-oxygen interaction, which was observed to be weakly interacted in the isopropyl alcohol-based material. For the chlorine 2P spectra, all the materials demonstrated an intense peak at 198 electron volts, which is assigned to the chlorine 2P 3/2 spin interaction due to chloride ions, while the chlorine 2P 1/2 peak, appearing at 200 electron volts, was also weakly absorbed in the isopropyl alcohol-based material. For the titanium 2P, peaks were observed at 458, 464, and 471 electron volts, which are ascribed to the titanium 2P 3/2, titanium 2P 1/2, and the titanium satellite peaks, respectively, which revealed the presence of titanium oxide in the material, while for the tungsten 4F, it displayed a weak peak at W4F 7/2 peak in the water-based material and was strongly absorbed in the ethanol-based material and absent in the isopropyl alcohol-based material. This peak occurred at about 13 electron volts and could be attributed to tungsten metal. However, in all the materials, the tungsten peak were observed at 35 electron volts, 37 electron volts, and 41 electron volts, all corresponding to the W4F 7/2, W4F 5/2, and tungsten oxide loss fixtures, which are also accounting to the different oxidation states in tungsten oxide. The thermal properties of the heterostructures reveal three substantial stages of weight loss, which could be due to the decomposition of different components in the material. The weight loss at less than 100 degrees Celsius is due to the loss of absorbed water molecules at the first stage, while the second stage of weight loss at temperature greater than 100 to about 243 degrees Celsius could be the decomposition of the labile oxygen-containing functional groups and intermolecular bonds. In the third stage of weight loss at temperature greater than 384 degrees, a residual mass of 81%, 97%, and 62% were found in the water, ethanol, and isopropyl alcohol-based materials, respectively, and these weight losses could be due to the denaturation of the materials. For the XRD pattern of the heterostructured composites, it reveals diffraction peaks which are prominent at 2 theta is equal to 6.9 degrees, 10.4 degrees, 10.6 degrees, 25.4 degrees, 29.4 degrees, and 32.5 degrees, which are in coincidence with the 001, 101, 200, 302, minus 502, and minus 405 HKL values revealed in the standard XRD database according to JCPDS file number 360101. Furthermore, for the optical and photochromic property of the materials, which was monitored using UV-visible spectroscopy, all the prepared tungsten oxide heterostructures, they optically change from white to blue under the UV light source, and the UV spectra of the materials before irradiation did not show an absorption peak, which could be due to the relaxation of the electrons and holes in the compound. However, after 10 seconds of UV light irradiation, there was a sharp electronic transition, giving rise to an intense absorption, which was captured at 787 nanometers. In all the materials, the water-based heterostructure displayed the fastest color formation after 10 seconds of UV light irradiation, which could be due to strong hydrogen bond interaction in the compound, thereby facilitating a photo-induced intermolecular long-range electron transfer process. Now, these observed electronic transitions could be due to the pi to pi star and n to pi star electronic transitions, which could be responsible for the formation of the blue colored centers in the compounds. So at the different irradiation time, there was also a corresponding hyperchromic shift, which could also be ascribed to the formation of the photo-generated electrons and holes in the conduction and the valence band, respectively. From the tax plots, it shows that the optical band gap energy of the material revealed photon energy of approximately 1.6 electron volt in all of the materials. However, the photon absorption coefficient differs significantly across all the materials. More also, since the heterostructures are typically semiconducting transition metal oxide, there is a likelihood of charge transfer due to the distinct intense absorption peak in the visible region of the UV visible spectra, and the plausible type of charge transfer could be from the orbitals of the deep eutectic solvent, which is acting as the ligand site, to the empty orbital of the metal site, which is otherwise known as the ligand-to-metal charge transfer. In this case, the narrow band gap energy between tungsten and titanium, coupled with the high oxidation state of the metal sites with empty low-lying d orbitals, are readily available to receive electrons from the filled 2p orbitals from the combined nitrogen and oxygen pair in a deep eutectic solvent. However, the efficient promotion of electrons for the highest occupied molecular orbital to the conduction band will trigger a high sensitivity of the charge transfer complex in the visible region of the spectra, thereby producing the photogenerated oxygen radicals for color development. More also, the electrochemical impedance spectra of the material displayed a higher conductivity in the water-based compound due to the presence of dispersed inorganic ions in the material that can interact with the ionizable molecules. Meanwhile, since ethanol and isopropyl alcohol do not produce dissociable ions, the observed conductivity in these materials were quite low. And in addition, the UV visible reflectance spectra of the materials demonstrated broad reflectance peak at 786, 783, and 719 nanometers, which corresponds to the water, ethanol, and isopropyl alcohol-based heterostructures at different irradiation time, revealing 59% reflectance, 32% reflectance, and 22% reflectance for the different material. This result could imply that the absorption of energy responsible for the excitation of photons emitted to the external environment is highest in the ethanol-based material. Thus, it could observe and reflect more light energy. For the morphological characterizations, the water-based material showed a surface morphology with uniform stripes that are embedded with unevenly dispersed spherical and cubic structures, while the ethanol-based material displays non-uniformly distributed and aggregated rod-like particles, as well as irregular shaped cubic particles in the isopropyl alcohol-based material. The observed differences in the surface morphology of the materials show that the different co-solvent solutions could differently influence the mobility of the electrons in the particles of the material, which could give rise to electronic absorption and color formation. The EDS spectra and the elemental mapping also revealed the oxygen and nitrogen species were uniformly distributed in the compound, and they could be responsible for the transport of mobile electrons and hole for the photoredox reaction in the heterostructures, as revealed in Table 1 below. Furthermore, the transition electron microscopy images further reveal the aggregation of the particles in the compound, while the selected area electron diffraction pattern further confirms the monoclinic structure of the tungsten oxide doped with titanium oxide made materials with good crystalline morphology. This could mean that the co-solvent enhance the surfactant and particle size control of the fine materials. For the BET surface properties of the material, it was observed that the material demonstrated a type 2 and type 4 isotherm, which is typical for non-porous or macroporous materials. More also, the materials displayed an hysteresis loop due to unrestricted mono-multilayer adsorption. The specific surface area obtained for the materials was 1.109, 2.486, and 0.017 meters square per gram, and the pore volume were 0.006, 0.015, and 0.0016 per G for the water, ethanol, and isopropyl alcohol-based heterostructures, respectively. These results suggest bulk materials whose porosity may be altered by the co-solvent possessing different hydrogen bond strength in the materials. More also, the defect structures observed in the materials could act as sites for entrapping photogenerated holes and electrons, giving rise to colored centers in the material. Overall, the isopropyl alcohol-based compound possessed low surface area to volume ratio, and this could be responsible for the poor color formation due to the weak absorption of the irradiated light on the surface of the materials. In conclusion, this study examined the fissile preparation of tungsten oxide doped titanium oxide heterostructures, and these heterostructures were fissilely synthesized using deep eutectic solvent templates of choline, chloride, and urea, as well as water, ethanol, and isopropyl alcohol as co-solvents for the extended hydrogen bond donor. The investigation of the structures of the material shows strong hydrogen bond interaction and the presence of all interacting functional groups, as was well observed in FTIR studies. However, the XPS studies shows weak peak in the IPA, which is the isopropyl alcohol-based material, which could greatly impact the reduction in the functional properties of the corresponding material. The thermal studies revealed 3 substantial stages of weight loss and high thermal stability of the water and ethanol-based materials due to strong hydrogen bonding and compactness of the well-interacted metal sites in the material. Moreover, all the as-prepared heterostructures optically change from white to colorless under UV light source irradiation after up to 120 seconds of irradiation. Meanwhile, the UV spectra of the material demonstrated a sharp electronic transition, giving rise to an intense absorption peak at 787 nanometers, which could be attributed to pi star and n to pi star electronic transitions. Considering that the heterostructures are typically semiconducting transition metal oxide and the distinct intense absorption peak in the visible region, a ligand-to-metal charge transfer electronic transition leading to color formation is also possible. The promising results obtained in this study could open new insights for the development of photochromic materials, optical display devices, and materials for glass, window, and door coating. We want to thank the Natural Science Foundation China and the Innovative Projects for Graduate Students of Southeast University for supporting this work. Thank you for your audience.